Thank you, Anna, for the introduction. Thank you all for being here, and thank the organizers for this wonderful thematic program. And I will stop now with the acknowledgements because I just have 20 minutes. For those who don't know me, I am Tom Szwagier. I am a third-year PhD student at INRIA under the supervision of Xavier Pennec. And today I will talk about a work that is at the intersection between statistics and geometry, which is entitled The Curse of Isotropy. So we have this widely known method that is widely used in data science, which is principal component analysis. So basically, you have a data set, you compute its covariance matrix, you take the eigenvectors associated with the highest eigenvalues of this sample covariance matrix. Together, they span a subspace that can be used for dimension reduction. This is how PCA is mostly known, but you have to know that the eigenvectors themselves, which are called principal components, are also highly used by applied scientists for data interpretability. And there is actually a whole chapter dedicated in the reference book from Jan Jolife on the interpretation of principal components. So I'm not an applied scientist myself, so what I'm going to say is to take with a pinch of salt, but let's consider a few examples. In this example from the book of Jolife, he considers a data set of morphological anatomical measurements from a class of students. So we have measures for the size of the hand, for the height, and so on and so forth. What he does is that he takes the first principal component associated with the highest eigenvalues. He then represents this principal component as a function of the original variables. It's the so-called loadings of the principal components. And then the idea is to interpret those coefficients to kind of interpret what are the main trends and the main patterns of variability in the data. So we can do, like with a kind of thresholding, a more simple representation of those loadings. And we can see, for instance, that the first mode of variability is positively correlated with all the measurements. So this could be interpreted by the fact that the main mode of variability in the data is the overall size of the student. It varies from the smallest student to the highest student, let's say. The second component, it makes more like a trade-off between the size of the hand and the height. So it will mean that the second trend of variability is between tall people with small hand and small people with large hand. And we can draw similar kind of analyses and conclusions from other anatomical measurement data sets. It has been done on fossil teeth data, for instance, with important outcomes. And also maybe an example from another field is in climate science. It's actually, PCA is actually highly used by applied scientists in climate science. And the principal components in data sets consisting in like sea level pressure measurements at the surface of the Earth can be related to climatic shifts pattern. So they are highly used, highly interpretable, and so yeah, PCA is still used a lot actually in many applied domains. So I hope I have convinced you that principal component analysis is an important method and that it is highly used. And what we do in our recent preprint, The Curse of Isotropy, is that we raise an issue about the interpretability of the principal components whose eigenvalues are relatively close. As we'll see, they can actually suffer from a large variability, a large rotational variability, which is a pitfall for data analysis. So in this context, we'll propose to transition from ill-defined principal components to more interpretable principal subspaces. Okay. So I will first present this issue about principal component analysis that we call the curse of isotropy. Then I will dive into the statistical methodology and geometric methodology to spot this issue in principal components analysis in practice. Then I will describe a few experiments. And finally, I will have a large list of perspectives, and I will dive into it depending on the time I have. Okay, the curse of isotropy. Imagine you have a data set that has been sampled from a Gaussian density. You look at its covariance matrix. If all the eigenvalues are distinct, then to each eigenvalue, you have a unique associated eigenvector up to the sign. Now, if you have an eigenvalue that is multiple, then to this eigenvalue, you have an infinity of eigenvectors associated, spanning a whole multidimensional eigenspace. It means that if you sample some points from such a density, you will have an infinite variability of the associated principal components. And as we said, it is a pitfall for data analysis because applied scientists literally interpret those principal components. And with that, we just see that if we draw two independent samples from the same distribution, the principal components might have nothing to see. So it's really like it makes the interpretation not stable at all. If you have a follow-up to summarize, it is that if we assume that the data has been sampled from a Gaussian distribution with multiple eigenvalues, then in this case, we have this important interpretability issue that is called the curse of isotropy. Now the question is why and when should we assume that our data has been sampled from such a distribution? The Gaussian assumption is really classical in statistics. It's due notably, as Xavier explained, to central limit theorems or to the entropy maximizing properties of Gaussians. So it's a very canonical assumption. But the more interesting assumption is about the repeated eigenvalues. And this is motivated by the so-called law of parsimony in statistics, also known as Occam's razor. The simplest explanation is usually the best one. As we will see, a Gaussian model with repeated covariance eigenvalues is more simple than a Gaussian model with distinct eigenvalues. So in this context, if we have a covariance eigenvalue profile with eigenvalues that are relatively close, we'll be tempted to equalize them so that we reduce the number of parameters while not hurting too much the accuracy of the representation. So this is the idea. And now we'll go into the methodology. So this will be 3 slides, a bit more mathematically heavy, but after you will have an opportunity to catch up with a summary. Okay, no animation. Okay. Okay, no problem. So it's a bit heavy, sorry. Principal subspace analysis, it consists in a Gaussian model. A Gaussian model where the covariance eigenvalues are repeated. They have pre-specified multiplicities. And the multiplicities define the so-called type of the model. If I can, no, I can't, okay. Sorry. The so-called, the sequence of eigenvalue multiplicities is what we call the type of the model. So here on the right, we have a principal subspace analysis model of type 2, 2, 4, 7, because they are the multiplicities of the associated eigenvalues. In this context, since it's a Gaussian density, we can compute the likelihood of the model with respect to its parameters, which is nothing but the probability of the observed data under our model and its parameters. So since it's a Gaussian density, it can be easily computed. And then there is this stuff called maximum likelihood estimation, which is at the basis of most machine learning optimization algorithms. It is given a data set, we want to find the parameters that are the most likely to have generated the observed data. And so we have a theorem for that. We can compute this, the solution of this optimization problem in closed form. And basically, it is that we take the sample covariance matrix of our data, then we compute its eigenvalues and eigenvectors. So up to now, it's like PCA. But after, what we do is that we block average the eigenvalues according to the pre-specified type of the model, so that it follows a kind of piecewise constant profile. And for those who might know it, there is a quite famous paper from Tipping and Bishop called probabilistic PCA, and our model generalizes it. Okay, and now it works. Okay, so there are a lot of geometers in the room, so I could not avoid a geometric analysis of the model, but I can go much more in details if you want in the questions. Basically, we want to know the geometry of the parameter space. So what are the parameters of our Gaussian distribution? They are its mean vector, which lives, let's say, in R to the power of P. There are the D distinct eigenvalues, which are assumed to be decreasingly sorted. So this is defined more like a convex cone of dimension D. And then we have the associated eigenspaces, whose multiplicities are defined by the type. And it happens that since we have a symmetric matrix, the eigenspaces are mutually orthogonal. And the space of all mutually orthogonal subspaces of pre-specified dimensions defines a so-called flag manifold. So Blanche mentioned it last week about the varifolds. And we can say a lot about the geometry, but basically, the geometry of the parameter space is perfectly well described, and we can compute its dimensionality, which is a very important quantity in statistics to assess the complexity of the model. So we P for the mean parameter, D for the D distinct eigenvalues, and the remaining, actually, it corresponds to the dimensionality of the eigenvector manifold, which is nothing but the orthogonal group, to which we subtract kind of the complexity of the fact that we equalize some eigenvalue, and so instead of eigenvectors, we have some eigenspaces, and so we remove some rotational degrees of freedom. So as we can see, the more eigenvalues we equalize, the lower the complexity. And it's actually quadratic in the number of eigenvalues we equalize. So we are tempted to equalize the most eigenvalues possible. And last but not least, principal subspace analysis model represented by their type. They describe a stratification of the space of a covariance matrix by the multiplicity of the eigenvalues. So this can be represented by a Haas diagram. On the top node, we have the most complex model, the model of type 11111. So all the eigenvalues are assumed to be distinct. This is well if we have an infinite number of samples, since we can perfectly estimate all the parameters of the eigenvectors and the eigenvalues of the covariance matrix. But on the other side, if we have a small number of samples, we don't want to fit a too complex model to risk to overfit some parameters. So we can take the model of type 5, which is the one where the 5 eigenvalues are all equal, so it's nothing but an isotropic Gaussian. So it says that we don't have a lot of samples. We can just say roughly what is the variance of our data, but not the orientation of the eigenvectors. So in the middle, we have a lot of other models, and the idea is, given a data set, we would like to make a trade-off between the... okay. Mine. Cool. No problem. Okay. So what we can do is that we want, given a data set, we want to fit a model that well represents the data, but at the same time is the least complex possible. And we have an important criterion for that, the BIC, Bayesian Information Criterion, which was also mentioned last week, which makes a trade-off between those two quantities. And we can play with it. And in the end, I won't detail the computation, but with that, we managed to a result that is maybe the most important result you should remember about this talk, which is that when we have two eigenvalues whose relative distance is lower than a certain threshold, depending on the number of samples, then we should assume that they are equal. So this threshold as a function of the number of samples is represented here on the right. We have that if we have 1,000 samples, then all the eigenvalue pairs with a relative eigengap lower than 21% should be assumed equal. So if I rephrase it, if you have an eigenvalue of 1 and an eigenvalue of 0.8, then you need at least 1,000 samples to distinguish them, which is rarely the case in practice. And we tested it on many datasets, from the many classical datasets, like from the UCI machine learning repository, for instance. And we see that most of the eigenvalue pairs cannot be distinguished. So the red cases correspond to the eigenvalue pairs whose relative distance is below this threshold. So there is a high impact on the analysis of the datasets. Okay. So now is the moment to catch up if you didn't follow the math. Our methodology is very simple. You have a dataset, you do the eigenvalue decomposition of the sample covariance matrix, and then you equalize the eigenvalues that are below the relative eigengap threshold. It's a gross summary, but it's the idea. And then you can wonder, so now we don't have any more principal components, we have principal subspaces, so how to give an interpretation to them? And we had a few ideas. Basically, you can sample some points from the principal subspaces and see how they look like to make an analysis of the main subspaces of variability in the data. But you can also apply some kind of factor rotation methods, like a varimax rotation, entropy rotation, so that we get inside the subspace some directions that are more interpretable than the original principal components. So we did a lot of experiments, but maybe I will just go fast on one. We have a data set. We compute the sample covariance profile. We can see that the eigenvalue 2 and 3 are relatively close. We equalize them. 5 and 6 the same, 7 and 8 the same. And then we have some principal components that are on the top row of the middle part. Then we perform a rotation within the subspace they span, and we can see that we recover some kinds of so-called like Laplacian eigenfunctions, which are the ones that are expected. And this would not maybe have been seen directly if we just looked at the principal components. So here the rotation helps the interpretability of the principal components. We did that also on a phase dataset, and it is actually funny because so what we say in the idea of the curse of isotropy is that you may have an invariance by rotation of the principal components. And there is something that when you have a face which is like that and another face which is like that, the average of the two faces is not a face like that. It is somebody with two faces because it's a linear space. It's a non-linear space. So basically, in general, when you do PCA on a dataset of face images, you have very fuzzy principal components. And if we look at the degenerate eigenvalues, the relatively close ones, and we perform a rotation within the subspace they span, we can recover much more interpretable face movements. Okay, so it was the conclusion of this part. And now I have 2 minutes to dive into to the perspective. So this one I won't detail it, but basically our results rely on the Bayesian information criterion, which is a widely used criterion for model selection. But actually it has some limits because it relies on many approximations. So there is an idea to extend the computation and kind of refine this criterion based on the very famous paper from Thomas Minka for principal component analysis. So it's a work in progress, but basically we have a better criterion than the BIC for performing model selection and knowing which groups of eigenvalues to equalize. Also, we can go beyond Gaussian distributions because principal subspace analysis is more for Gaussian distributions. So we already investigated Gaussian mixture models. So for that, we have to design a kind of expectation maximization algorithm, but it's a bit more complex. We have to include model selection in it, so it's a bit more tough. And we can also go towards other distributions, but in this case, the maximum likelihood estimation might involve some kind of Riemannian optimization, and the model selection might be complicated, so we might more do a kind of stratified optimization, but it's also like some works in progress or to appear. And last but not least, so I missed a wonderful night at the oldest amusement park in Vienna because of that. So it's a preprint that I wanted to put online before this talk. It's called the flag trick, and basically it's related to just what I said before, but if I want to present it shortly, you have a lot of methods in machine learning that try to look for a subspace that best represent the data. So this involves somewhat an optimization on Grassmannian manifolds. And many methods fall into this category, like linear discriminant analysis, spectral clustering, robust subspace recovery, etc. And the issue is that, in general, you don't know the dimension you want to try, so you try several ones. And the issue is that for different dimensions, the optimal subspaces are in general not nested. They are not, the smallest one is not included in the largest one. And this raises an issue of consistency that we detail in the paper. And we propose to solve it by lifting the Grassmannian optimization problem to flag manifolds. So we specify a sequence of dimensions we want to try. We use kind of nested projectors, and we optimize over the space. And this yields the so-called flag trick, which can be performed then with Riemannian optimization on flag manifolds. So the preprint is out since this morning, so I invite you to look at it. Thank you very much.